Hello, this is Hanul Sung from Seoul National University. I would like to introduce our efficient HPC storage management system. The contents is as follows. Parallel file system, comprised of many HDDs, has been a foundation of storage tier of HPC systems. As computational capability has grown over 1 petaflop, a large number of system components have been used in HPC systems, thereby causing increased overall system failures. For a fail-safety purpose, HPC applications aggressively utilize checkpoint and restart, the most common fault tolerance mechanism. This causes the checkpoint to dominate about 80% of I/O traffic of HPC system and significantly generates bursty I/O, which is difficult for PFS to handle. To alleviate the issue, burst buffer, which is composed of high-end flash SSDs and a high-speed network, has been introduced as a new storage tier between compute nodes and PFS. Recently, there have been many efforts into merging burst buffer with PFS. As the cost per bit of flash is falling, it becomes possible to replace HDDs with low-end TLC SSDs. NERSC announced that the next supercomputer with an all-flash storage system, called Perlmutter. Therefore, it is expected that a new all-flash HPC storage system with integrated burst buffer and PFS will be widely adopted in the near future. We believe that the new system has high-end SSDs such as NVMe SSD as burst buffer for performance and low-end SSDs such as TLC SATA SSD as PFS for capacity, and they are placed on the same node. However, there is a severe problem in the new all-flash HPC storage system. Burst buffer and PFS are located on different nodes, and PFS consists of HDDs in the prior HPC storage system, so substantial performance differences offered by burst buffer and PFS. Therefore, HPC users prefer dedicated burst buffer allocation method for a whole lifetime of their HPC applications to avoid access to PFS as much as possible. But this allocation style causes severe underutilization of expensive burst buffer resources. In addition, there is no data management methods between burst buffer and PFS for HPC storage systems. Data management is the responsibility of users. To handle this problem, we proposed new BB allocation method and data management method. The dedicated BB allocation method, which is used for prior HPC storage systems, make the burst buffer wasteful for two reasons. First, some users eagerly request BB resources for I/O errors prevention, performance scalability. And the users manage data movement between BB and PFS, so users want to get large capacity of BB to prevent complicated data movement between BB and PFS. They ask up to 6 times capacity even when they actually utilize only little portion. 5% of BB per hour is used according to the logs from NERSC Core. Second, burst buffer stays idle for most of the time because of characteristics of checkpoint and restart. Since HPC applications use BB only for I/O phases, burst buffer does not be used for the rest of the time except for the I/O phases. Checkpoint that dominates I/O traffic of HPC system is requested scarcely, such as once per hour or some minutes, and thereby resources of BB are wasted most of the time. Moreover, large capacity is required for data durability of checkpoint. However, in the new HPC storage system, PFS is placed with burst buffer in the same node, and it consists of a high-speed network and low-end SSDs, which significantly reduces the overhead of PFS access. So it is not worthwhile to use dedicated BB allocation method with penalty of BB underutilization. For this reason, instead of the dedicated BB allocation method, we need a new BB allocation management and a novel data management method between BB and PFS. So, we analyze characteristics of checkpoint and restart, which is representative of HPC applications. First of all, HPC applications run for a long time to solve computationally intensive problems and perform checkpoint at a particular cycle to avoid recomputations from scratch. For this reason, the total amount of the checkpoint written to BB by the applications for a certain period is kept quite steady. As so, It is possible to predict the total amount of the checkpoint written to BB with previous ones. Second, each application has its own checkpoint period. Thus, each application accesses the BB differently during a certain period. Third, HPC applications keep multiple versions of checkpoint for data durability. HPC users have a tendency to keep the old versions of checkpoint without deleting them even though only the most recent version of the checkpoint file is required for restart. Since each user requires different reliability, each application has a different number of checkpoint versions. Fourth characteristic is that HPC applications have different failure rates. Failure is caused by individual components, such as processors, disk, memory. Since failures of a single component are rare, the large number of the components unavoidably leads to frequent failures. Lastly, there is no locality across the checkpoint files of HPC applications unlike normal data. Temporal locality does not exist across checkpoint files, because the checkpoint file is requested only when in failures. Since a new checkpoint file is created in every checkpoint period, the same checkpoint file is not constantly used unless the application has multiple failures within a single checkpoint period. Also, spatial locality does not exist across checkpoint files. The failure of an application does not affect the failures of the others because each application has different failure rates. So checkpoint files of other applications will not be requested, even if they are stored around a checkpoint file which is accessed due to a failure. Based on analysis. Unlike the dedicated BB allocation method, the BB oversubscription method allocates more space to applications than the total capacity of BB by allowing the applications to use only in the I/O phase, not the whole lifetime. So applications in the computation phase should yield BB to other applications in the I/O phase via demotion from BB to PFS. Therefore, a data management approach between BB and PFS is required. There are many proposed approaches for multi-tiered storage systems, but they are not suitable to use for the new HPC storage systems. For the first reason, the existing approaches use static demotion threshold without considering the amount of data to be moved between storage tiers. With the prior approaches, demotion is only operated when BB is idle before reaching the threshold. When the used capacity of BB reaches the threshold, demotion is operated concurrently with checkpoint. If the number of users using BB increases, the amount of checkpoint also increases, causing a decrease in BB idle time. If the BB fills up when the existing approaches identify hot and cold checkpoint files using basic algorithms based on data locality, such as FIFO, LRU, and hotness aware. However, since checkpoint files across applications do not have the data locality, it is inappropriate to apply the basic algorithms for selecting cold checkpoint files. HPC applications have their own checkpoint period and keep multiple versions of checkpoints. With FIFO algorithm, although old version checkpoints for an application with low checkpoint period are stored in BB, the latest checkpoint with high checkpoint period can be chosen as a cold data. This makes BB inefficient and leads to low restart performance. Also, a checkpoint file is needed only in case of failure. Since a new checkpoint file is created every checkpoint period, it is very unlikely that the same file will be reused multiple times. Therefore, LRU or hotness-aware algorithm leads to the low efficiency of BB. Moreover, since there is no spatial locality between checkpoint files near a failed file do not need to be prefetched or left in BB. The failure rates also need to be considered since HPC applications have their own failure rates. Without taking the failure rates into account, checkpoint files with high failure rate might be chosen as cold data, not checkpoint files with low failure rate. Based on the characteristics of checkpoint and restart, we propose a new demotion approach for high and stable checkpoint and restart performance. First of all, we can predict the total amount of the checkpoint written to the BB for a certain period, so we can also decide maximum amount of data needed for demotion to avoid checkpoint performance degradation caused by demotion execution. Based on them we adjust demotion threshold and demotion speed adaptively. Second, each applications have different failure rates and the number of versions of checkpoint. So we utilize failure rates and version-aware victim selection for demotion. This figure shows the overall architecture of BBOS. It is composed of I/O engine and data management engine and an in-memory key value store for efficient engine process. The I/O engine, the core of BBOS, has 4 modules. Throttler adjusts demotion speed dynamically and demotors copy data from BB to PFS. We evaluate our HPC storage management approach with 8 compute nodes and a single storage node for BB and PFS. For BB, we use 4 800GB NVMe SSDs with the sequential write and read performance up to 920 MB per second and 3200 MB per second. For PFS, 4 4TB SATA SSDs are installed. The compute nodes and the storage node are connected with a 100GB switch. We use cluster file system for both BB and PFS and configuration is tuned for high performance. Also, BBOS is implemented by modifying cluster FS and adding some developed modules. To validate our system, we compare BB utilization and checkpoint restart performance with Data Warp, one of the current HPC schedulers which use the dedicated BB allocation, and 2 policies of Harmonia which is the only scheduler that uses a BB over subscription method. Since Harmonia is not an open source, we make an emulation based on the paper. MaxF aims to optimize the BB system efficiency by maximizing the BB utilization. Because the policy wants to maintain high capacity of available BB, it always demotes data at full speed even when the checkpoint is performed concurrently. On the other hand, MaxBW aims to provide maximum checkpoint bandwidth to applications. With this policy, the checkpoint and the demotion are not performed at the same time. To compare BB utilization with each approach, we assume that each application requests 80 GB checkpoint once a period. Then we count how many applications can finish the checkpoint within the period. Data Warp allocates BB capacity as much as users desire with a dedicated BB allocation method, so BB utilization is 100% in the best scenario. MaxF shows high BB utilization because it performs demotion with maximum demotion speed. And since MaxBW needs to ensure maximum checkpoint throughput, it shows lower BB utilization than MaxF. BBOS performs demotion by adjusting demotion threshold and speed, so it shows the same BB utilization with one of MaxF. To validate BBOS, we execute experiments in various situations with different scenarios for total amount of data written to BB and I/O job congestion. When I/O job congestion pattern is low and med, there are enough to finish I/O jobs, so Data Warp shows high throughput and low latency. But, with high congestion pattern, Data Warp shows very low throughput due to concurrent execution of I/O jobs, because there is no I/O job scheduling. MaxBW always shows high throughput, since it does not execute demotion during checkpoint execution. However, MaxBW shows severe performance fluctuation, because applications have to wait to prevent I/O interference and to stop for making space in BB. MaxF shows the lowest checkpoint throughput because it demotes data at the highest demotion speed. But, MaxF performs demotion in advance for BB not to overflow, so it does not stop I/O jobs, resulting low performance fluctuation. BBOS improves BB utilization with the oversubscription method. BBOS shows lower performance fluctuation without enough idle time than MaxBW. BBOS shows lower throughput with enough idle time than Max, and BBOS shows higher throughput than MaxF with enough idle time. MaxF always demotes data at full demotion speed and it takes longer to process the checkpoint, which makes the next I/O jobs to wait longer. Therefore, MaxF shows higher latency than BBOS, even though it performs demotion more aggressively than BBOS. BBOS performs demotion in advance like MaxF, but it adjusts threshold and speed of demotion. As a result, BBOS provides high BB utilization and stable high checkpoint performance. We measure the hit ratio of restart on BB in order to compare restart performance. We compare LRU and FIFO algorithms used in most HPC data management with BBOS. We executed experiments under various total amount of data written to BB and mean time between failures. Since HPC applications does not have data locality, LRU and FIFO show different results every experiment. However, BBOS always shows higher restart performance than others, and BBOS shows increased hit ratio as the variance gets higher. And we measure hit ratio of restart on BB including version-aware victim selection for demotion with 3 checkpoint period. Version-aware demotion shows higher restart performance. In summary, BBOS provides high restart performance by adopting victim selection method based on characteristics of checkpoint and restart for demotion. We proposed BBOS for the new all-flash HPC storage system based on characteristics of HPC applications. We utilized BB over subscription allocation method instead of dedicated BB allocation. And we managed data placement between BB and PFS. As a result, it improves BB utilization up to 2.2 times compared to most popular dedicated BB allocation method, and provides stable and high checkpoint and restart performance.